Your stakeholders have confident opinions about what users want, what drives engagement, what's working. You've got data. But when instinct clashes with evidence, how do you cut through the noise? Well, the chi-square test won't shout. It just quietly reveals the patterns hiding in plain sight. And sometimes those patterns change everything. Let's learn more. Hi, everybody. I'm Dr. Chad, and welcome back to my course, Quantitative Research for Qualitative Researchers. If you've watched all of my videos to this point, you've learned a lot. You've learned all about how to build great data visualizations and my 5 basic rules for creating principled viz. You've learned how to identify a research question, how to measure your variables, how to do descriptive statistics and univariate analysis, and even how to do A/B testing and the basics of the null hypothesis testing framework. You've demonstrated these skills through creating a principled bar graph showing the distribution of names by gender in the baby names dataset, by creating a principled line graph that shows when the name Beyonce was most popular, by defining what it means to be good at football, by measuring the effect of adding an animation to Jiramisu on conversions to Jiramisu layered and learning how to share these results with interested people, and performing a t-test on Jiramisu data and learning how to talk about statistical significance. That's a lot to even say, let alone learn in such a short amount of time. I just want to say great job, everyone, and I'm excited to learn even more today, so let's get started. I want to take a minute to reiterate how much you've actually learned in this short amount of time. This is a lot of knowledge, and it puts you well on your way to knowing enough to be dangerous with quant methods, especially if this is combined with a solid qualitative toolkit. This is an amazing start. I do want to point out, though, one of the keys to learning is to actually use some of these lessons somewhere. When I was in academia, best practices were to introduce a concept on Monday, walk through it in an interactive lesson on Wednesday, and then let students lead it on Friday. This gave you a chance to see something, follow along with hands-on practice, then lead it in a hands-on exercise on Friday. Lots of good reinforcement of building skills and building a good practice. That, of course, is difficult in the real world where we have jobs and a lack of structure provided by school, but there are a few ways you can do this. Try to apply these techniques in your work, probably with support from someone with a bit more experience in quant research, who can make sure you're not missing any of the key points your first few times doing something new. You can apply these techniques in a passion project. What interests you? What do you want to learn? What is fun for you? Figure out ways to do some R programming and statistical analysis on something you care about. Take a minute, comment on this video, let me know if you're interested in a cohort-based approach with some more hands-on learning. At some point, I'm thinking about offering a class with personalized instruction and a cohort to learn with, so I'd love to hear if there are people who'd be interested in that. And a quick ask for all of you. I put out a lot of content here for free, and I hope you find it valuable. If you do, please do me a favor, subscribe to my channel so I can start hitting the metrics I need to start monetizing my channel and get some of the money I spend on production back. If you really like the videos, share them with a friend, click that like button, and go back to my older videos, watch them start to finish. All these things really help me grow, which is really important to me. But enough of that, let's get to the main video, and let's keep learning. Today, we're going to go further in the world of bivariate analysis, or analyses that have 2 variables. We've already talked about A/B testing a bit, but we started in a world where someone had already designed a study for us. That's not a very likely scenario, so today we're going to take a step back and look at how we can create our own bivariate analyses from scratch. The idea behind bivariate analyses is simple enough. We're just moving from 1 variable to 2 variables. Easy enough, yes? But if we think about bivariate analyses, it's really where we start jumping into the world of telling stories, generating real insights, and being able to do hypothesis testing to get that magic concept of statistical significance. This is a big jump and an opportunity to really level up our game. So I want to start with saying something my Meemaw used to say. Doing a proper bivariate analysis starts well before we open a spreadsheet. We need to go through the basic steps as we build. What have we observed? What is our best hypothesis about what we observed? How can we express this in a simple, clear way? I want to really stress this third point here. If you cannot express your hypothesis as X goes up, Y goes up, or as X goes up, Y goes down, then you're really not ready to start collecting data. One of the worst things you can do is to collect your data and not have it match what you actually wanted it to do. You end up with a big mess. You wasted time, you wasted energy, you wasted money, wasted credibility, all the things. So really think about clear, strong hypotheses. You don't necessarily have to validate those hypotheses, but at least if you start that way, you get the right output, whatever that is, whatever the truth is. For more on this, you can watch my video about setting up research questions and operationalizing variables, but for now, let's go ahead and get back to the main stage. I've worked with a lot of people who like to build surveys and think about what questions do we want to answer and then ask those questions on a survey. But that's really only the first step. Knowing customer NPS score is helpful, I guess, but when you find out that your NPS score is 55, what have you learned? More importantly, what do you do with this information? What recommendations do you make to your product teams? How do you make impact? This is where those bivariate analyses can come in handy. If we have a second variable that we can measure against NPS, we can start to really learn more about our product and what we should do. When you're designing a survey, it's tempting to look at everything separately. Satisfaction here, income there, education up here, but real stories don't live in isolated numbers. Real stories are about relationships, about how two things come together to create meaning. Think about questions like, what age group responds best to our product? Or how does gender affect NPS score? Or how does frequency of use affect our NPS score? These start to get into a world of being closer to insight, closer to telling stories, and closer to making actionable product decisions. This is actually surprisingly uncommon when we design research, and I'm often surprised how many times I see talented researchers who miss that step and only focus on what the top line descriptive statistics are going to be. The good news is, you do this type of analysis in your head all the time. When you're going to the grocery store and you pick a line, maybe you look to see how many customers are in the line and pick the shortest one. When you try to pick a movie to watch, you look at reviews on Rotten Tomato. When you think about whether you're going to buy a car, you think about how much you liked your previous car of the same type. These are all bivariate analyses and ones you're familiar with. Our brains are wired to spot relationships and patterns between things. Quantitative analysis just gives you a structured way to do what you already know how to do intuitively. We've already done a little bit of this in a previous video tracking the frequency of the name Beyonce. We measured the frequency of naming a child Beyonce and compared it to her big album releases. We found that more people named their child Beyonce in big moments in her career. We learned about the connection between pop culture and people's behavior and how much that shapes identity. That's the power of bivariate analysis, finding the stories hidden between the lines. So now that we've talked about the theory, let's get into some of the tools we can use to help you see the connections in your data, whether it's comparing averages, checking trends, or visualizing relationships. How you do this depends on the types of variables you have. Are they categorical or continuous? This probably deserves a whole video, but until I do that, I did want to spend a minute or two talking about the different types of variables just to make sure we all have the same glossary of concepts as we go forward. The first type of variable we're going to talk about here is a categorical variable. A categorical variable is a type of variable that represents distinct categories or groups. These variables can take on a limited number of distinct values, each corresponding to a different category or label. These values are not numeric, and the categories do not necessarily have any inherent order or ranking unless they're specifically ordinal variables, which we can talk about in another video. Categorical variables are often used to classify data into different groups based on characteristics or qualities. Some examples of categorical variables include gender, something like male, female, non-binary; marital status, single, married, divorced, widowed; color, red, blue, green; type of car, sedan, SUV, truck. These are obviously not exhaustive, but these are a list of kind of some of the things you might have. And then categorical variables themselves can be divided into nominal, which are categories with no inherent order, like color or type of car. And then ordinal, which are categories with a meaningful order, but the intervals between them are not necessarily equal. Something like education level, having a high school degree, bachelor's, master's, doctorate. Those are the types of variables we'll be talking about today in this video, so I want to focus on those, but there are also continuous variables. A continuous variable is a type of quantitative variable that can take on an infinite number of values within a given range. These values can be measured with increasing precision and can include any value between 2 points, including decimals and fractions. Continuous variables are typically represented on a scale, and their possible values are not limited to specific separate points, but can vary smoothly across a continuum. Some examples of continuous variables include something like height. So you're 5.4 feet tall, 5.435 feet tall, 5.43532 feet tall, etc., etc. Weight, you're 150.2 pounds, 150.23 pounds, 150.235 pounds, etc., etc. You get the point. Temperature, 20 degrees, 20.5 degrees, 20.555 degrees. Time, 2.5 hours, 2.55 hours, 2.555 hours. You get the point. I've said a lot of these words here, but you understand the idea. So back to the main stage, leave a comment, let me know if you'd like a longer video getting into these concepts in more detail. So today, we're gonna talk about the case where you have two categorical variables. We'll use the chi-square test of independence. The chi-square test of independence is about comparing observed patterns in your data with what we'd expect if nothing special is going on. That is to say, if the two variables were completely independent of each other. When we start, we assume that the two variables are independent. In other words, there's no relationship between them. This is what we call the null hypothesis. As an example, let's say you're looking at two groups, chefs and restaurant owners, and whether or not they like a specific feature in Jiramisu, our very real project management software for chefs. The feature in question, an animation of someone throwing espresso powder up in the air. What does this mean for the expected distribution? If chefs and restaurant owners are independent, we'd expect the distribution of preferences for the animation feature, liking it or not, to be roughly the same across both groups. In other words, knowing whether someone's a chef or a restaurant owner should not influence whether they like the animation. Let's break it down. Imagine you surveyed 100 users of Jiramisu, 50 chefs and 50 restaurant owners. 60% of the respondents to your survey said they liked it, while 40% didn't. If the feature and group are independent, we'd expect 60% of both chefs and restaurant owners to like the animation, and 40% of both groups to not like it. For example, for 50 chefs, 50 restaurant owners, we'd expect 30 chefs like the animation, 20 do not. Similarly, 30 restaurant owners like the animation, 20 restaurant owners did not like it. In this case, there's no difference between the two groups, so we cannot conclude that chefs and owners have different preferences here. We fail to reject the null hypothesis. But what if the two groups had different preferences? The alternative hypothesis states that the two variables are not independent, that there is in fact a relationship between them, and in this case, we'd expect to see a difference between the two groups. As an example, if the chefs and restaurant owners do not have the same preference for the animation, this suggests knowing someone's role, chef or restaurant owner, could give us a clue about whether they like the animation. What does this look like though? Well, the observed distribution in each group, chefs versus restaurant owners, will differ from the expected distribution. For instance, maybe 40 chefs like the animation, but only 10 don't like it. Meanwhile, 20 restaurant owners like the animation and 30 restaurant owners don't. If this is the case, the distribution of preferences between chefs and restaurant owners is not equal. Chefs are more likely to like the animation than restaurant owners are. But how can we do this mathematically rather than just the eyeball test? Well, to do this, we calculate the chi-square statistic. At its core, the chi-square statistic is a way of quantifying how much the observed distribution of categories differs from the expected distribution under the null hypothesis. If the data match what we'd expect under the null hypothesis, the chi-square statistic will be small, and we'd expect to be unable to reject the null hypothesis. If the data significantly differs from that expected distribution, the chi-square distribution will be large, and we'd expect to be able to then reject the null hypothesis. Thinking about the Jiramisu example again, we can eyeball that if the group is split at exactly 60-40, then those are clearly exactly the same, and we're not going to reject the null hypothesis. But what if one was 62-38 and the other was 58-42? Is that a big enough difference? 65-35 and 55-45. Where does it become enough for us to expect to reject the null hypothesis that the groups are equal and support the idea that the two groups are different? That's exactly what the chi-square test is for. Your stats program will do this for you, but I want to walk through the logic. The process for calculating statistical significance in a chi-square test is incredibly similar to any other null hypothesis testing calculation. You evaluate the difference between the observed data and what the data would look like if there was no relationship, and then consider the sample size you've seen. You're more likely to be able to reject the null hypothesis when the differences between observed and expected data are high. The sample size is high as well. Easy enough. Fits nicely with our framework of null hypothesis testing we talked about in the past. So what does that look like if we actually programmed it in R? It's fairly straightforward code, easy enough to execute. All you do is you take a data frame with two categorical variables and then some frequencies, and you turn it into crosstabs using the xtabs command. The xtabs function in R creates a contingency table by cross-tabulating variables. The formula count tilde group plus response means use the values in the count column to fill a table whose rows are defined by group and columns by response. In other words, it tells R sum the count values for each combination of group and response. It's kind of like pivoting a spreadsheet. Excel people, you know this life. You're telling R which variables to use for rows and columns, and which columns hold the numbers you want to summarize. Once we've done that, we do the actual chi-square test, which is as simple as just typing chisq.test parentheses table underscore data. This gives us pretty simple results: a chi-square value, the number of degrees of freedom, and a p-value. If that p-value is less than 0.05, we can reject the null hypothesis. This is good evidence that the two groups, chefs and restaurant owners, have different experiences with the tiramisu innovation, which is exciting for us because we can share this with our stakeholders and make product impact. Life is good. So that of course begs the question, how do we communicate these results to stakeholders? One way that's easy enough is just sharing it in a 2x2 table. I know I've spoken badly about tables in the past, but they do have their place. If you want, you can check out my short on visualizing the EPL table for another example, but this is a good chance because it's simple enough to visualize 4 cells. It's only percentages, which people are relatively comfortable reading, and a 2x2 table is enough of a visual to orient most readers. Something simple enough like this can work. You have a table here, you show chefs are more likely to enjoy the tiramisu animation than restaurant owners. Chefs, restaurant owners liked, didn't like, 75, 45, 25, 55, n equals 150, group differences are statistically significant, p is less than 0.05. Something simple enough like this can work. We've got a nice title here, chefs are more likely to enjoy the tiramisu animation than restaurant owners. We've got the difference between chefs and restaurant owners, we've got the difference between liked and didn't like the animation, we've got the sample size, we've got some statement here that group differences are statistically significant at p less than 0.05. This shows everything you need to know. It's pretty easy to read, it's pretty easy to see. I think most people can understand this. This is one way of doing it, and one way I think I'm pretty happy with. So if that's how you want to do it, go ahead, you have my blessing. But here at the Dr. Chad Auditorium, we are graph enthusiasts. So there's always the classic option of a bar graph showing the percentage of people who liked the animation in each group. Just a simple comparison of 75% for chefs, 45% for restaurant owners. My interns are in the back preparing a simple graph showing this. We won't go through the code in too much detail. You can see that in the introductory video in this playlist, but let's go ahead and take a look at what a principled graph looks like here. So this right here is actually really nice. It's really clean. The interns have done well. It meets our 5 principles of good graphs, and most importantly is very easy to understand when you share it with your stakeholders. Remember that your goal is to use your technical expertise to make recommendations, but those recommendations must be understood if they're going to be adopted. So something like this is very clear, very concise. This is a 5-star graph here. I approve. There is one more option to visualize here, and that's stacked bar charts. It's interesting because AI recommends this pretty consistently whenever I ask it about chi-squared tests, and I could see cases where it's useful, but it's really not my preferred choice because it can get pretty messy and pretty ugly really fast. Maybe it's better if you have more than a 2x2 table, maybe it's better if you have more categories of interest. I don't know. I find stacked bar charts noisy and visually displeasing, but that's just me. In the interest of completeness, I wanted to show them here. So if you take a look at what the interns have done, this shows a percentage of chefs saying yes and no, and then the percentage of restaurant owners saying yes and no. You can look at this and compare the two groups relatively easily, although to my mind it gets into the whole humans aren't good at seeing area problem that pie charts suffer from. It's not bad, but not great in my opinion. Another maybe more common way you will see these is as a horizontal bar chart. And we can do that in R by just using our simple bar chart code, typing chord flip with parentheses, so it rotates the axis basically 90 degrees. Let's take a look at that. So this is maybe a bit easier to process and is more common in my experience, so I wanted to show you this option as well. If you like it, you'll be in good company and no one will criticize you for doing these graphs. It's just not my preferred option, especially for something simple with only 2 options of 2 categories. Why spend ink if you don't have to? I'm a very you know me, I follow Coco Chanel's principles of keep it simple, remove one item whenever you can. So that's my thoughts. Reasonable people can disagree. I did want to expose you to all the options though, so you can really see it and have a complete toolkit. So with that being said, let's go back to the main stage and wrap things up. So let's wrap things up here. We learned a lot today. You now know how to do a new kind of bivariate analysis, one with two categorical variables, and you know the intuition of the chi-square test, how to calculate an R, and how to present results in a visually pleasing, easy to understand way. Great job, everybody. I know every channel says this, but make sure you subscribe to my channel. I do want to say I'm pushing to get some key numbers to help grow my channel, and you can really help me do that. Keep the content coming. So like this video, share it with your friends, keep watching the rest of the playlist, leave it on in the background, let the thing go in the background, the numbers will go up, life will be good for me, you'll learn a lot by osmosis even. Win, win, win. Thanks everybody, and I'm looking forward to seeing you next time at the Dr. Chad Studio.